Hello, this is Colin Selleck of Binghamton University. This lecture is for ME 391, Measurements and Instrumentation, and today we're talking about vibrations. Earthquakes are vibrations. Vibrational analysis was first used in the 1920s in California to study buildings' behavior in earthquakes. They wanted to improve the building resistance to damage by earthquakes. And the earthquakes generate two kinds of waves. P waves, where the motion is parallel to the wave motion, and S waves, where the motion is perpendicular to the wave motion. So let's look at this little movie here. So this is a P wave. The motion is parallel to the wave motion. And that's an S wave. The motion is perpendicular to the wave motion. Vibrational analysis is needed for many applications. For instance, machinery needs to be isolated for the comfort of the building occupants. Telescopes must be isolated from vibrations to ensure image quality. And vibrations from long trips in trucks and other transportation vehicles can be a problem, as bolts have been known to come unthreaded. And lastly, the study of vibrations is crucial to designing automotive suspensions. In the 1940s, many aircraft were needed for World War II, and the development of increasingly complex instruments and higher air speeds drove the need to test instruments before flight certification. So as you're probably aware, there's a lot of vibrations in airplanes, and so they had to develop a way to test the avionics before they put it into the airplane. And so they developed this thing called a shaker table. They're used to model vibrations, and they're designed for testing electronic or mechanical components. Rockets used for space vehicles and satellites undergo extreme vibrations during launch, as well as when the pyrotechnic devices detonate, for example, at staged separation. So the payload needs to be able to withstand these vibrations. And let's take a look at Dr. Miles' research. He's a vibration expert.
Sound is basically it's a propagating wave that's small fluctuations in pressure, and your ears pick up these very, very small pressure fluctuations and turn it into what you perceive as sound. I've spent a lot of the past few years designing microphones for hearing aid applications based on studies of insects. A whole lot of what you hear in any situation is really strongly affected by where you are and how reflective all the surfaces are in your room. The chamber is designed to just suck up all sound, and it sits on springs, so it's not directly connected to the rest of the building to keep it as quiet as possible. It's something that we spent a lot of time designing, and it met our specifications by far, and is really one of the quietest places you can go. We go into this chamber and we set up our microphone that is placed on a 5-degree of freedom robot, and we can control the position of that microphone using the computer that's on the outside of the chamber. And we can place that microphone anywhere we want inside the chamber with millimeter accuracy. And with that, through computer control, you can scan sound fields. We also have a loudspeaker where we can play out sound. Once we set it up and plug it into the patch panel on the wall, we walk out of the chamber, shut the doors, turn out the lights, and then take the data outside. This is a really tremendous opportunity for our research, and it also enables us to expand the kinds of research that we do. And it's opening up a number of new opportunities for us.
So biomimicry is basically imitation of biology, right? Scientists have long used plants and animals as a basis to study and develop new medicines or new ways of doing things. And so Dr. Miles was studying this fly because, well, I'll just show you the video.
Helen Keller said, when you lose your eyes, you lose your ability to see things, but when you lose sound, you lose touch with people. Sound is communication. It can help calm us down. Certainly music and the quality of sound is really important to us. At an extremely early age, I was really interested in sound. There's something about sound that really connects with me. This whole project started where I was asked by some biologists to help them understand the hearing in a very, very small fly. What we ended up finding out was that this fly has eardrums. Most flies don't. So it was having found that in nature, when the animal is not huge, yet it needs to tell where sound comes from, it used a certain sort of principle. By taking the ideas that we got just from the mechanical study of how these flies' ears work, we realized, that could be turned into a very tiny microphone. The truth is, discovering how the fly works was easy. Taking that idea and turning it into a working device where instead of nature doing it, now it's us. That was way harder. The device that we've been working on is intended to help people who have hearing impairment or may use hearing aids understand speech when they get into a noisy environment. There's this little dark rectangular silicon chip that actually contains the microphone itself. We put it in this aluminum box just because we don't want to get our fingers all over the microphone diaphragm. Our microphone is very directional down to much lower frequencies. At this point, we have done the research to demonstrate that the concept works. In engineering, in creating products, showing that it can be done in the laboratory is only the first step. And the next step is even harder. There are a lot of other electronic devices could benefit greatly from having a very small directional microphone. For example, your cell phone. Many students have been involved in my research from undergraduate through PhD level. And the truth is, the most important outcome from this project has been the education of all the students who have been involved in it. If you're an engineer, you can create things that can be very, very helpful to people. It's really rewarding to work on something that helps people a lot.
So the reason the biologist asked Dr. Miles to take a look at this fly is this fly is very unusual. So it lays its eggs in beetles, and it locates the beetles by sound. But its ears are so close together, how can it possibly do that? So that's what Dr. Miles was studying, and that's why he was studying this particular fly. Vibration may be caused by nearby traffic, subways, building mechanical systems, or simply normal human activities such as walking across the floor. This vibration does not jeopardize the building's structural integrity. However, while the actual movement may be minimal, human perception of motion is significant. And so vibrations can be disturbing to building occupants. And here you see a shaker table basically, and they're testing two different building models. Analysis of vibration modes is a critical component of a design, but is often overlooked. Structural elements such as complex steel floor systems can be particularly prone to perceptible vibration, irritating building occupants or disturbing sensitive equipment. Inherent vibration modes and structural components or mechanical support systems can shorten equipment life and cause premature or completely unanticipated failure, often resulting in a hazardous situation. Detailed fatigue analysis is often required to assess the potential for failure or damage resulting from the rapid stress cycles of vibration. Vibrations can be torsional as well. Torsional vibration is the angular vibration of an object, commonly a shaft along the axis of rotation. Torsional vibration is often a concern in power transmission systems using rotating shafts or couplings where it can cause failures if not controlled. So let's take a look at this video on torsional vibration.
In this module, we will discuss torsional vibration. This topic builds on many terms introduced in Module 1, namely natural frequency, resonance, and dynamic forces. All rotating equipment, including compressors, engines, and pumps, will experience a torsional load. One important torsional load is the gas load inside the reciprocating compressor. The gas load acts on the piston and is transmitted to the crankshaft. This chart illustrates the gas load from all the cylinders during one revolution of the crankshaft. Another important load is the inertial load, due to the weight of the piston assembly. Inertial load for all cylinders also varies widely over each revolution. By adding together the gas load and the inertial load, we find the combined torsional load for all cylinders in this compressor. The load from each cylinder acts on the crankshaft, resulting in a torque that can cause vibration problems. Each machine will have a unique load profile. A torsional vibration analysis considers how this combined load interacts with the crankshaft, the engine or motor, the coupling, and the resulting stress and vibration on the system. A complete drivetrain or torsional system, for example, a reciprocating compressor with a coupling and an electric motor, has a torsional natural frequency, or TNF. Torsional natural frequency is defined as the frequency at which a shaft twists back and forth. Imagine twisting a shaft by rotating one end. After releasing the shaft, it rotates back and forth. This oscillation occurs at the torsional natural frequency. This is analogous to the mechanical natural frequency described in Module 1. Torsional vibration can occur, especially if the system is resonant. In this example, the vibrations are low at 900 RPM. As the speed increases, the system becomes resonant at 1200 RPM when the speed is at the TNF. At resonance, the vibration response is greatly amplified. Above the resonant frequency, vibration response is significantly reduced. The torsional analysis must accurately predict resonant conditions and vibration problems. If not, the results can be catastrophic, destroying couplings, broken compressor shafts, broken motor shafts, not to mention the downtime and cost if the unit is inoperable for 1 to 2 months. Torsional vibration is often called the silent killer because a failure like this occurs without warning. The best way to mitigate these failures is to order a torsional vibration analysis before a unit is built. With early involvement, the system can be modified more cost-effectively and easily than later, changing the coupling size or style, adding a flywheel, or a detuner, and changing the shaft material or size are all easily done if the components haven't been built. If the system is already built, then needed modifications are often more expensive and complicated, resulting in delayed delivery of the unit. The next time you are involved with ordering or designing a rotating system, it is highly recommended that you have a torsional analysis performed. This module is a brief introduction on torsional vibration analysis. The key points are that torsional vibration can result in failure. A torsional vibration analysis should be performed very early in the package design phase. The analysis should adequately cover the entire operating condition envelope, including upset conditions, while addressing tolerances in manufacturing and installation. For superior accuracy and practical recommendations, please contact Beta for your next compressor or pump project.
So as you can see here, we have a cantilevered I-beam. It undergoes horizontal vibration, torsional vibration, and compressive vibration. This is the first mode, and the second mode, as you may know, has 2 nodes in the wave, and this is the second mode, horizontal, torsional, and compressed. There also exist other kinds of vibrational modes in which the beam gets compressed or stretched out in the height, width, and length directions, respectively. We also have vibrating membranes. A 2-dimensional elastic membrane under tension can support transverse vibrations. Think of a drum. The properties of an idealized drum head can be modeled by the vibrations of a circular membrane of uniform thickness attached to a rigid frame. Due to the phenomenon of resonance at certain vibrational frequencies, its resonant frequencies, the membrane can store vibrational energy, the surface moving in a characteristic pattern of a standing wave. This is called a normal mode. A membrane has an infinite number of these normal modes, starting with the lowest frequency 1, called the fundamental mode. So let's take a look at this vibrating membrane.
Here's the lowest frequency vibrational pattern in a circular membrane. This circular membrane is a piece of thinnest rubber dam stretched over a short length of PVC pipe and held in place with some rubber bands. In this lowest pattern, the entire membrane moves up and down together as one piece. The whole thing goes together. Here's the second pattern. The same membrane occurs at a little bit higher frequency. Half of the membrane moves up while the other half is moving down, and there's a line right across the diameter called a node that doesn't vibrate at all. Here's the third pattern. The membrane, there are 2 sections, actually it's kind of like a cloverleaf pattern. 2 opposite sides of the membrane move up together and the adjacent sections move down. So there's 4 regions that move alternating up and down.
Vibrational analysis can also be used in analyzing wind loading on buildings. Especially the skyscrapers in New York City, they have to be very careful about the vibrational modes due to wind loading. This is the Taipei 101 in Taiwan. It's the world's tallest building, I believe. And to counteract the vibrational modes from earthquakes, for instance, they had this tuned spring mass damper system out to the very top of this tower. It's 600 tons, and it's 5.5 meters in diameter. That's metric tons. Here's one that's here's a spring mass damper on the Hancock Tower in Boston, Massachusetts. It's offsetting wind loading. Now, spring mass damper system, you may have studied this in physics. We have a mass M, a spring with a spring constant K, and a damper has a damping coefficient of in newtons per second per meter, newton seconds per meter. Basically, what this damper is, you can imagine the center is filled with oil, and the piston has holes drilled in it. So as the velocity increases, the pressure will increase and the force will increase as well. We can do a analysis on the spring mass damper system by drawing a free body diagram. We have the mass, we have Kx, the spring force, and Cx dot. X dot is the rate of change of x, and that's the damping force. And so we get this second order differential equation. The solution is this. Don't worry about this equation, but it is a exponentially decaying cosine function. So first I want to talk about something that's called the logarithmic decrement. So here is a oscilloscope trace of a decaying vibrational mode, decaying cosine wave basically. And the logarithmic decrement is denoted by the letter delta, and is equal to 1 over n times log of the amplitude of the first wave divided by the amplitude of the nth wave. So you can see the wave numbers here, 0, 1, 2, 3, 4. So you take the height of the 0 wave, this height right here, and then you count out as many waves as you can, and perhaps the fourth wave you'll take another height value there. So n in this case will be 1 over 4. N would be 4, so you have 1/4 the log of the ratio of the amplitude of the first wave to the amplitude of the second wave. You will be needing this equation in the experiment. Let's talk about the damping ratio. Zeta is defined as the ratio of damping coefficient C to the critical damping coefficient C sub C. So the critical damping coefficient occurs when zeta is equal to 1. And knowing the logarithmic decrement that you discussed in the previous slide, you can use this equation right here to calculate the damping ratio. Now, a damping ratio of less than 1, that's the blue line here. The system oscillates, but it slowly comes to rest, right? So it goes past 0, then it goes past 0 again, and it just slowly dies out. At the critical damping ratio in the green line, when zeta is equal to 1, we have the no oscillation whatsoever, and the system comes to rest as quickly as possible, right? And if the system's overdamped, there's no oscillation, but the system returns to rest slower than for critical damped systems. So you can see that would be in the red line. So it doesn't have any oscillations, but it just takes longer to return to the 0 position. So for instance, when you're designing automobile suspensions, you want the suspension to have a damping ratio of 1, so it returns to normal as quickly as possible. And the system's not damped at all. You get the purple line, which is it just oscillates forever and never comes to rest. That's impossible, actually, due to frictional energy loss. But okay, so we have the undamped natural frequency. That is the natural frequency of the system without the damper, and that is equal to the square root of k over m. K is the spring constant, m is the mass. Now, the damped natural frequency, that means the damper is now introduced. The damped natural frequency is equal to the undamped natural frequency times the square root of 1 minus zeta squared. And remember, Omega has units of radians per second, and frequency is in cycles per second, or hertz, and you can convert between the two using this equation. Omega is equal to 2 pi f. The damping coefficients are defined by these two equations. C is 2 times the mass times zeta times the W sub n, which is the undamped natural frequency. And the critical damping coefficient can be calculated using this equation, 2 times the square root of k times m. The vibration experiment looks like this. We have a cantilevered beam. We have an actual strain gauge on here. You're going to be using strain gauges again. We have a DC motor, and we have a plastic disc attached to the shaft of that motor, and we put an eccentric weight on that shaft to induce a vibration at the end of the beam. So you're going to spin this disc at varying speeds. The weight's going to cause a driving frequency to be applied to the beam, exciting it to vibrate. And as the driving frequency approaches the beam's natural frequency, the beam displacement grows. This displacement will be characterized by the actual strain gauge, which is connected to an oscilloscope via a Wheatstone bridge. And by plotting displacement versus driving frequency, the resonant frequency of the beam can be determined. And here you see an example of that. The driving frequency goes up and up as it approaches the resonant frequency of the system, and then it drops down. Okay, that's the end of this lecture. See you in cyberspace.